What volcano ash actually is to understand how volcanic ash affects pH, we must begin with what volcanic ash truly is. Despite the word ash, it is nothing like the soft, powdery material created by burning wood or paper. Volcanic ash is a mixture of hard, abrasive, and chemically reactive particles formed from shattered magma and pulverized rock. When an eruption occurs, magma rapidly decompresses and fragments into glass-like shards. If water, either from groundwater, ice, or seawater, interacts with the magma, the violent thermal shock breaks it into even finer particles. The composition of volcanic ash varies dramatically depending on the type of volcano and its magma. Basaltic magma, common in shield volcanoes like those in Hawaii or Iceland, produces ash rich in iron, magnesium, and calcium. These minerals tend to be alkaline when dissolved in water. Conversely, rhyolitic magma, which fuels some of the most explosive eruptions, contains high levels of silica, aluminum, and acidic compounds that can lower pH when they dissolve. When ash rises into the atmosphere, it does not travel alone. Volcanic gases like sulfur dioxide, carbon dioxide, chlorine, and fluorine condense onto the ash surface. These gases are the key to understanding ash's pH effects because once they mix with water droplets in clouds, lakes, or rivers, they form a range of acids. Sulfur dioxide may become sulfuric acid, hydrogen chloride forms hydrochloric acid, and hydrogen fluoride forms hydrofluoric acid. These acidic coatings cling to the ash, meaning that when the ash eventually falls back to Earth, it brings both mineral particles and acidic films. How pH works in natural systems. pH is a measurement of how acidic or alkaline a substance is, based on the concentration of hydrogen ions in that substance. The pH scale ranges from 0 to 14, with 7 being neutral. Numbers below 7 indicate acidity, while numbers above 7 indicate alkalinity. Although the difference between a pH of 6 and a pH of 7 may seem small, the pH scale is logarithmic, meaning each step represents a 10-fold change in acidity. This is why even slight shifts in environmental pH can dramatically alter chemical reactions and biological functions. In natural systems, pH is constantly in flux due to interactions between minerals, water, bacteria, gases, and organic matter. Rainwater naturally has a slightly acidic pH of about 5.6 because carbon dioxide in the atmosphere dissolves into it, forming mild carbonic acid. Soil pH varies widely depending on the minerals present, organic matter, weathering rates, and local climate. Lakes and rivers tend to fall within a narrower pH range because aquatic life is sensitive to rapid deviations. For instance, fish eggs may die at pH levels below 5, and many species cannot survive above pH 9. When volcanic gases enter the atmosphere, they change the chemistry of airborne water droplets. Sulfur dioxide, one of the most common volcanic gases, reacts with oxygen and water to form sulfuric acid. In strong volcanic eruptions, this can drop the pH of rainwater well below 5, resulting in rainfall that is not just mildly acidic but highly corrosive. This explains why volcanic eruptions are known for producing some of the most extreme acid rain events ever recorded. However, the story is far more complex because volcanic ash does not only make systems more acidic, the minerals within ash dissolve slowly in water, releasing alkaline ions such as calcium, sodium, and potassium. These ions increase pH instead of decreasing it. This means volcanic eruptions create both acidic and alkaline environments depending on the timing, ash composition, and rate of water interactions. How volcano ash changes pH in water. When volcanic ash enters water systems, whether lakes, rivers, reservoirs, or even ocean surfaces, it triggers a cascade of chemical reactions. These reactions can begin within minutes and continue for decades, depending on the depth of water, the volume of ash, and the minerals present immediately after an eruption. The first major pH shift typically comes from acid rain. As volcanic gases dissolve in atmospheric moisture, they create sulfuric, hydrochloric, and hydrofluoric acids. When these acids fall with rain, pH levels in fresh water can plummet. Lakes that typically sit near a neutral pH of 7 may drop to pH 4 or lower. In extreme cases following historical eruptions, pH levels have temporarily fallen to 2.5, which is nearly as acidic as lemon juice. Such acidity can cause immediate ecological damage. Fish gills become damaged, amphibian eggs fail to hatch, and aquatic plants can die off. Acidic water also mobilizes heavy metals like aluminum and iron from surrounding soils. These metals dissolve more easily at low pH and become toxic to both plant and animal life. After the initial burst of acidity, the longer-term story reverses. As volcanic ash begins dissolving, alkaline minerals leach into the water. Calcium carbonate, magnesium-rich silicates, and sodium salts slowly raise the pH. Some lakes affected by volcanic ash have been observed to become highly alkaline, reaching pH levels between 9 and 10. Such conditions also disrupt ecosystems because few organisms are adapted to highly alkaline environments. How volcano ash affects soil pH and plants. When volcanic ash settles on land, the chemical transformation of soil begins almost instantly. But unlike water, where chemical changes can happen rapidly, soil systems undergo a slower, more complex evolution. Soil pH is shaped by mineral weathering, microbial activity, plant uptake, rainfall, and organic decomposition. Volcanic ash adds a new layer of reactive minerals and acidic compounds that interact with all these factors. In the first hours or days after ashfall, the pH shift depends heavily on ash composition. Ash with acidic surface coatings can temporarily lower soil pH, creating a more acidic environment. This can stress existing vegetation, especially crops that have narrow pH tolerance windows. Acidic soil pH increases the solubility of metals such as aluminum and manganese, which can become toxic to plants at high concentrations. Additionally, young seedlings and shallow-rooted plants may suffer from both chemical stress and physical smothering caused by ash layers. However, the longer-term story of volcanic ash in soil is overwhelmingly positive. As the ash weathers, it releases nutrients essential for plant growth, including potassium, phosphorus, calcium, and magnesium. These minerals gradually alter soil pH toward neutral or slightly alkaline, depending on the underlying geology. Over years, the weathered ash transforms into a soil type known as andesol, which is among the most fertile soil classes on Earth. This is why volcanic regions such as those in Indonesia, Japan, and the Andes support rich agriculture and dense forests. Why understanding ash and pH matters today. Volcanic eruptions are not rare in geological terms. At any given moment, around 40 to 50 volcanoes worldwide are actively erupting or exhibiting unrest. As human populations expand into volcanic regions, understanding ash chemistry and its effects on pH becomes increasingly important for public safety, agriculture, water quality, and environmental management. First, water supplies are at risk. Acidic rainfall after eruptions can contaminate drinking water, corrode infrastructure, and mobilize toxic metals. Monitoring pH shifts allows authorities to warn communities, shut down affected reservoirs, and provide alternative water sources. Long-term alkalinity increases also affect treatment processes, requiring adjustments to maintain safe drinking water. Second, agriculture depends heavily on soil pH. Farmers in volcanic regions must understand how ashfall will alter their fields. In some cases, acidic ash may demand liming treatments to rebalance pH. In others, ash may enrich soil with minerals, reducing the need for fertilizers. Knowing the ash composition becomes essential for making informed farming decisions. Third, understanding ash and pH interactions helps scientists predict ecological impacts. Lakes near volcanoes may undergo pH shifts that affect fish migrations, spawning seasons, and species composition. Rivers supply water to towns, farms, and hydroelectric systems. pH changes can affect these too.